السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله today we'll go through many subtopics that are very important for training. So the first one is data loss functions. We started to talk about data loss functions already last time. We talked about the multi-class classification task. The main point here that I want you to understand is that there are multiple loss functions, and for every task you should consider different loss function. So for example, this is the task that we saw before, the multi-class classification. The multi-class classification, we have multiple classes, but one of them only is the right one for every example, right? Like whether this article is political or sports or health, whether the sentiment of this review is positive or negative or neutral, one of them only will be true at a time. So the actual label actually is like a vector. All of the values, so this is the yi, all of the values are zeros except one is one, right? That's the output in a multi-class classification. And as we saw, if we have like four, so that if this is the hidden layer and there is the rest of the network, if we have four classes, then the output layer of the network will have how many units? If we have four classes, 4. Okay, so we have 4 units, and usually we apply the softmax layer so that we make sure that the output of these neurons sum to 1, and we apply the cross entropy loss function as we saw before. So this is what we saw before. A special case of it is binary classification. We have only 2 classes. So we can actually use only 2 neurons here in case of binary classification, but we can also use just 1 neuron. So in this case, the network will be, this is the last hidden layer, and this is the rest of the network, and there will be just 1 neuron at the output layer. And if that's the case, then we use the sigmoid function so that we can get a value between 0 and 1. So this will be very similar to logistic regression. Okay, so the output neuron will, in this case, will have an activation function which is the sigmoid function, and so it will look like the logistic regression classifier, and thus we can use the same exact cross entropy loss function that we used with logistic regression. It's just a special case of the multi-class classification. So actually these two we saw before, so nothing new, but just to remind you. The new thing is in this slide. This is a third task, or a different task from the multi-class classification task. And let me give you first one example application for this. Let's say that I have an image and I want to train a network that will tell me what are the objects in this image, like whether there is a cat or not, whether there's a dog or not, whether there's a human or not, whether there's a tree or not, whether there's a tree or not, whether there's a wall, whether there's a sky. Any object can appear in an image, right? So that means that in one image, in one example, we might have multiple classes actually. Okay, so this is called, that's why it's called multi-label classification. For every example, we don't just have one class, we can have multiple classes. So in this case, the output will be also a vector. The output, the actual label will be a vector, but in multi-class classification, all are zeros except 1. Okay, here all are zeros, but we might have multiple ones. Okay, because as I said in the example, we might have a dog, we might have also a cat, we might also have a human, right? So in each example, you might have multiple labels. Each example actually belongs to multiple classes. So this is called multi-label classification. We didn't define this task before, but it is one of the tasks that neural networks are good for. In this case, what will be the output layer for the network? Again, let's say that this is the hidden layer, the last hidden layer, and that's the rest of the network. Then the output layer, if we have, let's say, 4 objects only that can appear in the image, then we will have 4 units. Right. This is again similar to multi-class classification, right? But in multi-class classification, only one of them should be 1. Okay, that's the true label for them. For multi-class classification, only one of them in the true label will be 1. Okay, but in multi-label classification, some of them will be 1s, not necessarily only 1. So to account for this case, we will apply the sigmoid function on each. We will not apply softmax, because softmax layer will make the sum of them to be 1. But here the sum doesn't have to be 1. Actually, we might have multiple 1s. So we will apply the sigmoid function for each, because this will give us a value between 0 and 1 at each unit, which indicates whether this specific object, for example, appears in the image or not. Okay, so this is like there is a logistic regression classifier at each unit, at each neuron. Okay, so each neuron would be like a classifier by itself, and the output values that doesn't have to be to sum to 1. Okay, is that clear? So in this case, what should be the loss function? Now we said in the previous slide that we have a loss function for the logistic regression classifier, right? Here, every output unit or every output neuron is like a sigmoid, is like a logistic regression classifier. Okay, so the loss function will be just the sum over all of them. And this loss is the loss for each one of them. We'll just sum over all of them. This will be the loss for one example. Okay, so you see the difference between the loss function here and the loss function for logistic regression. For logistic regression, we just have one neuron at the output. Okay, because it's binary. It's either 0 or 1. We just have 2 classes. Here we have multiple classes, and some of them might be 1s, some of them might not. So each neuron can have a value between 0 and 1 that indicates if that object, for example, exists actually in the image or not, if that's the example. Okay, so we just sum the loss value over all the neurons. This is for multi-label classification. So again, what is the difference between multi-label classification and multi-class classification? For multi-class classification, only one class is true. Okay, in multi-label classification, we might have multiple classes, and of course, this will change the loss function. Okay, because the loss function for the multi-class classification will assume that all the output will sum to 1. Here, the output actually for each one can be between 0 and 1. So the sum is not 1. Okay, so this is a generalization for logistic regression. The last one, which I think we saw it very early in the course, is regression. Remember, what is the difference between classification and regression? The output is a real value. Okay, the output for regression is a real value. Type. In this case, let's say that we want to estimate the for a given student, we want to estimate the GPA for that student. It's a real number, right? Type. How can we model that, or how can we use neural networks to compute that? We'll use a network, and the output layer will have how many neurons in this case? Just one. Just one. So we have, let's say right here, we have, this is the last hidden layer. It's the rest of the network, and we just have one neuron in the output. And should we use any activation function? No, because the without the activation function, the output of the weighted sum is unbounded, and that's what we want in regression. Okay, so this is just will be one output. Of course, we can do regression on multiple functions, and you can learn multiple regression functions at the same time. In that case, we will add neurons to the output layer. What should be the loss function? I think we talked about it before. In regression, what should be the loss function? Do you remember? So in regression, the label will be the value, the actual value, right? And we have the predicted value, and what? There is no log. Why? Yeah, the sum of the difference square. Okay, so this is the this is the actual value, and this is the predicted value. This is f. So we'll just subtract them and square. So that's the loss for the regression task. Okay, of course there are many other loss functions, but these are just examples, common examples to be used. So as a summary, we saw binary classification. Okay, we saw also multi-class classification, we saw multi-label classification, and we saw regression. Okay, the main point is that for every task, the loss function can be different. Okay, depending on the meaning of the task. Okay, and depending on the and of course for each task you need to think how the output layer will be. Okay, because it depends on what you want to learn at the end. The hidden layers, of course, can be hyperparameters, the number of the layers and the number of units per layer. They are not fixed for a specific problem, but if I have, for example, a multi-class classification problem where I have 7 classes, then it's natural to use 7 units at the output layer, but you can try multiple values for the number of units at the other layers, except of course the input layer. Okay, any questions about this? Then we switch to another subtopic, which is regularization. Of course, we talked about regularization before, right? What is the objective of doing regularization? To avoid overfitting. Okay, to avoid overfitting. We discussed regularization in the context of linear models, but it was a general context. We talked about L1 and L2 regularization, if you remember. Still, we can use them in neural networks. It will be very similar, except that the weights here are the weights over the entire network instead of just the weights for the linear model as we talked about before. We can use L1 and L2. We can even combine them. As you see here, we can just add the L1 regularization to the L2 regularization. In this case, we have different parameters. Okay. So these are now hyperparameters. One that belongs to the L1 and the other belongs to L2. So we can tune them also, lambda 1 and lambda 2. And we can even combine, I mean, the combination also is possible, which is called elastic net regularization. You can add both. And it's not a must that we use this or that. We can actually use both. Okay? And we can even use a different type of regularization that is very common in neural networks, called dropout. So this is a completely different idea. Okay, so what is dropout? On the left here you see a full network, right? This is what we used to see. In dropout, during training of one example, let's say, for that will repeat of course for every example, but for one example, we will select a percentage of the neurons and we will drop them out. Drop them out means like deactivating them or removing them completely, as you see here in the figure on the right. Okay, so some of the neurons will be completely off. With every training example, we will select randomly a sample of the neurons and we will deactivate them. Right. How can we control the number of neurons that will be off? There is a parameter, okay, probability. So if, for example, P is 0.5, that means that 50% of the neurons will be deactivated for every example. If the probability is 50%, then 50% of the neurons will be completely off, will be completely deactivated. Deactivated here means that it's like we removed the connections, and we removed this connection completely. Okay, with the probability type. What is the intuition? If we remove this, okay, then if we remove with every example, then every neuron, of course, some neurons will be activated at one example and other neurons will be activated with another example, right? And so on. So every training example will see or will train different set or different subset of neurons. The intuition here is that I don't want overfitting, right? Overfitting means that the network will learn even noise. I want to train the network so that every neuron will see different subset of the training examples. So it will not overfit all of them because it will not see all of them. Okay, so if I drop some neurons every time I train with an example, then overall every neuron will be like learned from different subset of the training examples, not the same training set as a whole. Okay, so that will make it more robust to the noise because it will not see everything. It will tend to generalize better because it doesn't see all the training examples, but all of them saw all together, okay, but not exactly. Okay, you can see it also in a different way, that when we drop the, like for example this neuron, there should be a link here, right? When we drop this neuron, this will be like removing this link. Now if the output of that neuron was noise, then now this neuron will learn without that noise. Okay, so it will learn to be more independent of the output of the other neurons. That will make the network more robust to noise. Okay, it's like it will work even if the other parts of the network are not working. That's the main idea of Dropout. Is that clear? Clear now? Of course, because of this dropout that will happen with every example, that will make training faster because the computations will be less, right? So that will also have the positive effect of making the training significantly faster. Type. What happens during prediction? This happens during training, right? So during training, some of the neurons will be off. Type. How about prediction? What should we do in prediction? Should we also drop out some of the neurons during prediction? Why not? My time back to ask. Why not? They are already trained. Okay, so once training is done, خلاص, we have the full network, but خلاص, my trained. Okay, then we should use it for prediction as it is. Okay, we should not remove some of the neurons. We should not do any dropping out during prediction. Okay, we should use the full network during prediction. Okay. There is another version of dropout called drop connect. So instead of dropping a neuron, we drop a connection. Okay, again with probability. Okay, so now the probability will not be the probability of dropping a neuron, it will be probability of dropping a connection. Okay, that means that some connections will be dropped with every training example. So we'll sample from the connections instead of sampling from the neurons. So it's another option that is similar to dropout. Any question about regularization? Of course, there are other ways of regularization. We'll not have time to go through them. Maybe if we have a course on neural networks or deep learning in particular only, we can, of course, discuss that in detail, but this is just to give you an introduction. Any questions? All right, let's switch to gradient descent and variance. We know that the standard, or what we call vanilla gradient descent, works by going through all the training examples, computing all the gradients for them, accumulating them, and then update the model. So the update of the model, which means updating all the parameters here, the weights and the biases, will happen once after, after seeing all the training examples once. Okay, not with every training example separately. Type. What's the problem with that? If I go through all the training examples until before I update the model, that would be waste of time if the training set is very large, and that sometimes happens, that we have training set that is very large. Okay, so we will not update the model until we see all the training examples, which might be millions of examples. So that will make conversions slower, because we'll make updates very slow. Okay, type. To account for that, there is another version of gradient descent that is called mini batch. Instead of waiting until the end of all training examples, we will have batches. Okay, so we'll take a batch from the training example, like 16 example, and then we do the update after them. And then we have another batch, then we do the update, then a third batch, then we do update, and so on. So this is called mini batch gradient descent. So instead of waiting for the entire training set, no, we will divide the training set into small batches. That's why it's called mini batch. Small batches of maybe 32 examples, or 64, or 16. Usually it's a power of 2, so that it can fit within the memory. And do the updates after these small batches. Type. What is the idea, or why could that be good? The idea here is that, if you remember earlier, we used to say that the training examples are independent, are identically distributed and independent, right? IID. But in reality, they are not independent, of course. There is correlation and there is redundancy in the training examples. So the idea is that a subset, a random subset of the examples, can be a good approximation of the entire set. So why should I wait for millions if I can maybe take 1,000 and update and make it update? So that 1,000 can be an approximation. Okay, and if I do these updates, I might have faster conversions. I might converge. Converge means that the updates, the weights will be stable at some point, so the updates will be very small, much faster than waiting for the entire set of training examples. Okay, so that's the idea of mini batch gradient descent. Is that clear? The difference is clear? You have a question? مش مقنع. طيب ايه اللي مش مقنع؟ No, okay. Okay, so I think I got what is confusing here. طيب. Let's say that these are the training examples, okay? Let's say that this is the whole training examples, okay? For vanilla gradient descent, we will compute the gradients for each one, and then at the end update the weights. Okay, so this is vanilla gradient descent. For mini batch, we will take small batches and at the end of each batch we will update the weights. Okay, so we'll do the update here, we'll do the update here, we'll do the update here. Type. What is the difference between this and that? The difference is that here we update the model much more frequent than here. So we might here converge faster than here. And we might get conversions, we might not need actually to go through all the data. Okay, you got it now? Any other questions? Type. Now, what is the extreme of mini batch gradient descent? When the mini batch is just one example. Okay. Okay. Before that, let me. So this is just a definition that an epoch is going through the data once. Okay. This is just a definition of an epoch. It's one full round over the entire data. Of course, the mini batch size here is a hyperparameter that you can tune also. Okay, you can tune that, or you can just fix it to a specific number that is usually power of 2. Type. The extreme, as you said, will be the case when the mini batch is just a single example. So that means that we will make the update after every single example. Okay, this is called also online gradient descent. And if you remember this big picture figure that we saw before, then for every example we will do the gradient descent update. So the update of the weights of the model will happen after every example. Type. What's the problem with that? It will take time, of course, because we will have to update the model every example. If we have very large set of examples, that will make the training actually slower. Type, if that's the case, why should we use it? Yeah, if the data set is small, then this will be fine. It will not take a lot of time. And another reason is that we can use it for online learning, right? What is online learning? Yes, if you are getting examples in real time, labeled examples in real time, you can of course use it, because now you can, whenever a new labeled example or a new labeled set of examples are available, then I can make the update. Okay, so these are two reasons why we can use stochastic. This is called stochastic gradient descent. Okay, so three variants: the vanilla gradient descent, which is plain, we just update after the entire training set. There is also stochastic, when we update with every example, and there is many batch, which is more common, when we update after small batches of examples. So this is gradient descent. Then we switch to activation functions. I think you heard about activation functions before, right? When or where? In what? In perceptron. It was the 0, 1, right? But also in logistic regression, we used sigmoid, the sigmoid function. Okay, so the sigmoid function is also, was actually also used in neural networks. Remember, where is the activation function in neural networks? It's at every neuron, okay, except the output layer. So the sigmoid function was one of the very first activation functions that was used in neural networks. If you remember, it can take any number, any real valued number, and can give us a value between 0 and 1. Historically, it was used, but recently it is no longer used for two reasons. The first one, if you look at the sigmoid function, probably after this value, or let's say this value, the output of the function will be what? Here will be 1, right? And how about the gradient? 0. Okay, the gradient after, or if the input is greater than this value, the gradient will be 0. Type, how about if the input is less than this value? The gradient will be also 0. Type, is that a problem when the gradient is 0? Why? Yeah, if the gradient is 0 in gradient descent, that means that we will not update any parameters, because the updates will always be 0, right? So this will be like dead neuron if it happens, okay, because it will saturate. The gradient will be 0. Okay, so this is a big problem. When the local gradient is very small or 0, that means that there will be no update in the network, okay, which will make the network almost dead. So this is a severe problem. Okay, this is called vanishing gradient problem. Okay, when the gradient is very small or 0, that means that the network is not learning anymore. So that's a big problem with the sigmoid function. There is another problem also, which is less severe but still a problem, that the output of that function is always positive, right? It's 0 or more, right? And usually it's positive. Type, what is the problem with that? If we look at the neural network as a whole, if we use sigmoid function in everywhere with every neuron, that means that every neuron, the output of that neuron will be positive. Okay? Type, the output of that neuron goes to the neurons of the next layer, right? Right? Type, with weights. Now, if you remember, we have a weighted sum, right? We have a weighted sum gate that will sum all the incoming, will sum the multiplication of the weights and the output of the previous layer, right? Now, if all of the outputs from the neurons are positive, that means that all the weights will be updated in the same direction, either all positive or all negative. Because the output is always positive, the gradient can be positive or negative, so the updates will be all either positive, all of them, or negative, all of them. So that means that the entire network will either, the parameters will be either increased together or decreased together. This is called zigzagging behavior, which is not good in training. Okay, because we always prefer that some part of the network will be updated positively and some part will be updated negatively. Okay, it will learn different things. Okay, instead of going in one direction. So that's another problem with sigmoid. Type the fixing of that problem, or at least the second problem, is what we call the tanh activation function. If you look at this activation function, what is the difference between this and the previous one? Yeah, the biggest difference is that now the output of the function is between -1 and 1. Okay, so that solves the second problem, right? The second problem was that the output is always positive. Now the output can be sometimes positive, sometimes negative. So that will fix the second problem of sigmoid, but it doesn't fix the first problem. Still, we can have dead neurons with zero gradient. So the next version of the next generation of activation functions included what we call rectified linear unit, or radio. So this is one of the very commonly used activation functions now in neural networks, called radio. So radio fixed the problem of saturation on the positive side. Okay, so we have the function, the radio function takes the maximum of 0 and x. So any input, it will give either 0 if the input is negative, because the maximum is 0, or the same input if the input is positive. So it will be like a threshold. If the input is positive, then it will be the same. The output will be the same like the input. If the input is negative, it will be 0. It will be clipped. Okay. So do we still have the same saturation problem? We don't have it at the positive side, but we have it on the negative side. Okay. So still we have some possibility of saturation at the negative side, which will make the neuron die if it happens to output 0. Okay. If the input is negative. So the second version is called leaky radio. Leaky radio makes sure that there is non-zero gradient all the time. Okay, so there will be no zero gradient at all. On the positive side, if the input to the function is positive, then it will be the same. The output will be the same. But if the input is negative, then there will be a small negative gradient. Okay, and this negative gradient is a hyperparameter. So this is, instead of having maximum 0 and x, this will give us radio. Now we have maximum x and ax. Okay, where actually this is my a is negative. Okay, a actually it should be negative here, so that the slope will be negative. So we'll have a negative gradient if the input is negative. Yes. Good question. Okay, good question. But let me finish this and then we'll get to that. So did you get the idea here? We have, for both cases now, we have non-zero gradients. Okay, so we don't have this saturation problem. Now, to your question, why don't we have just a line? Yeah, is that non-linear now? Do we have a non-linear function, or is it linear? What we have now is non-linear, right? If we make it linear, then we're not. Then the function is non-linear completely. It's linear completely. Okay, so we are not learning much. It's like perceptron, yes. Okay, so we want the function to be non-linear so that we can learn better functions. If all the activation functions are linear, then the entire network is linear, and it's not different from perceptron. So that the decision boundary will be linear. We don't want the decision boundary to be linear. So it has to be non-linear somehow. Okay, and the activation function is the source of nonlinearity in neural networks. There is nothing other than the activation function that will make the network nonlinear. Type, why making the network nonlinear important? Yeah, because reality is nonlinear. Okay, reality is complex. Okay, the functions that we want to learn are not always, of course, linear. Okay, maybe rarely linear. So we really want to learn more complex functions, more complex decision boundaries. Okay. But to make this, no, this applies to any value of x. Oh, you mean if a is negative, then you are right. Then yeah. Then this should not be. You're right. Not able to erase it. I don't know why. Stuck. Type, let me solve it in a different way. Anyway, you understand. Okay? So yes, that should be positive. It shouldn't be negative. Yes, you're right. Any questions? Okay. The last subtopic, and this is this should be very quick, which is the weight initialization. What do you mean by weight initialization? What do you mean by weight? What is a weight? A parameter, right? Type. What do you mean by weight initialization? Yeah, what are the initial values we should assign to the weights? Remember, when we start training the network, each parameter should have a value. Okay. In Perceptron, we used to, if you remember the algorithm of Perceptron, how did we initialize the weights? Zeros. Okay. Type. Why don't we do that here? It's the easiest thing, right? Just update them, initialize them to 0. And go pray that it will learn in the last 10 days of Ramadan. What's the problem with that? But why do we care about? Let's not talk about zero initialization. Why do we care about initialization? Yes, because remember, we are optimizing, right? The initial value that we will start from will make an effect on the final minima that we will reach, right? The function is very complex. Okay, we might be stuck at local minima, so the initialization will make an effect. So initialization as a topic is important. Okay, type. Now zero initialization makes our life easier, right? Let's think together. If we make the initialization, yeah, Fatma. If we make the initialization to be zero everywhere, then what will make the neurons different from each other? You will learn the same thing, will be updated similarly, and they will be exact copies, right? Nothing different between them, right? I mean, the neurons at the same layer will all be the same, will all have the same values. Okay? Type. Do we want that? Of course not. We want each neuron to learn something different. Okay? So we should make the initialization different for each neuron, and it shouldn't be zero. Type. The idea here is that if we make them zero, as I said, there will be symmetry and everything will be the same, and we don't want that. We don't want to have symmetry. We have actually asymmetry. We want the asymmetry. We want the neurons to be different, okay? Because they will we will learn different things. Type. How can we achieve that? We will initialize one of the ways, of course, not the only way. Okay, one of the ways is to initialize the weights to randomly to small numbers. Instead of 0, we will randomly initialize every weight to a small number, maybe from Gaussian distribution. So we will break the symmetry in this case. We don't want symmetry in the network. We don't want all the neurons to be copies from each other. We want neurons to be different. So that the neurons, as I say here, will compute distinct updates and will contribute differently to the network. Okay, so this is the very simple idea of initialization. Of course, there are other ways. One of them also, it's a bit different from the random initialization, is to say, okay, we will initialize all the weights to zeros except small fraction. So for every neuron, we'll select like 10 connections and we'll make them non-zero, okay, by random initialization to small numbers also. Okay, so either random all of them or some of them will be non-zero by selecting a fixed number of connections for each neuron. So this is called sparse initialization. But how about the biases? If we do that with the weights, can we initialize the biases to zeros? And if we initialize the weights to non-zero values, then yes, of course, we can initialize the biases to zeros. That will not be a problem. They will not be copies because the weights that are associated with them are different. Okay, so we can simply use zero bias initialization. In some cases, it is preferred not to do that if we are using radio, for example, just to make sure that the output will not be zero. Okay, so we might fix the values of the biases to non-zero value, small value like 0.01, as we see here, just to avoid that the output of the neuron is zero. But generally, we can assign it to zero. Okay. These are very quick ideas about training neural networks. Of course, as I said before, there is lots of details. Okay, just the very simple ideas we discussed here. There are other really more complex details, and this, as I told you before, this field is very hot now. Lots of changes over time. So if you are interested, you have to really be up to date. Any questions? Type. The last thing that we will not spend time on is, as you see here, is a playground, right? So this is a demo called the Neural Network Playground. Unfortunately, we don't have time to go through it, but I would encourage you to go through it. So what is this? This is a website where you can try architectures of neural networks. You can add neurons, you can add layers, you can remove layers, you can see the output of the neurons, you can change the input, you can play. It's like a really playground of neural networks. This is really fun. I want you to go through it. Okay, so I leave the link to you. But actually, we don't have time to do it now. Type. Anything else? Are we done? Are we done? Yes, we are done, and I would like to start with what I started. I would like to end with what I started with, which is this one. That should be our objective, our goal, and I hope that we achieved it. I hope that you really learned what can benefit you. I hope that what you learned in this course really will benefit you in your further studies or in your work. Whatever your future endeavor is, I hope that you learned something useful. And remember always also this intention. Okay, we are doing that for this, especially in these days. I hope that this is what we really achieve at the end, inshallah. One quick note that my machine learning, by the way, is not my specialty. I came to it because it intersects with my own specialty, which is information retrieval. There is lots of machine learning ideas in my field. I came to be really interested in the field. I wanted to learn more about it, so I proposed to teach it. I proposed the course, and then I taught the course, and that's where I came to machine learning, actually. But my specialty is different. But I hope that you really learned something useful, you benefited from the course. I really enjoyed, I always enjoy teaching machine learning, maybe more than my specialty. Not that much, but I really enjoy machine learning courses. I learn a lot from your questions, and that's why I'm open to any questions at any time. Don't worry about me bugging you sometimes, but I really like to get questions and answer those questions as much as I can, and that's why I learn. I really learn from your questions, by the way. Sometimes you force me to think about something that I have never thought about. It's not my specialty, so I didn't think about all possibilities. So when you ask me questions, sometimes I really take some time to think about them and answer. So I learned this way.